much better.
Great.
Okay.
Thank you.
So I want to talk about JWST, mainly because I've been involved in it in various forms since '98. So and I'm still involved with JWST. So everybody knows what this is. I've got a bunch of slides. Some I'll go through fairly quickly. Won't read all the details on it, but I gave that you've got a hard copy of all the presentation slides, so that'll be good to refer to at some point in the future. So everybody knows what this is. This is Hubble. On the last day when it was after the final servicing mission on May 19th, it was so that's the last picture that we've seen of it right after servicing. And so the question is okay, what's next? And so what actually is next started back in 1985. 5 years before we launched Hubble, NASA headquarters, as well as a bunch of scientists in the community, got together to start thinking about what do we want to do after Hubble. It's hard to believe that was 5 years before we even launched Hubble, but it was. And so that's when Next Generation Space Telescope, now called James Webb Space Telescope, started to get some ideas as to what we're going to do and why. And of course, why is, let's see, this should go here. Which do I point at? Point it that way?
Point it at the computer.
Didn't work.
Well, it worked before.
It worked before. There we go. All right. So what's after Hubble? JW is the scientific and technological successor to Hubble. It's got to look back to the very first stars and galaxies that were formed. Therefore, it's got to be in the infrared. It's 6 times more collecting area than Hubble, 100 times more sensitive, 1,000 times more sensitive than Spitzer, which is our NASA's previous infrared telescope in space. It's got to operate cold. The best part about it is I can use the pointer. There's a guy. I actually drew this to scale years ago. There's a person. I don't know whether it's 6 foot or not, but as a person. There's Hubble. There's JWST, fully deployed. So it's much larger than Hubble, no doubt about it. And so we started working on this back in the early mid-90s, started really working on it as far as coming up with what the right plan was. It's an infrared telescope. It's got to be cold. So it's operated at 40 Kelvin, not room temperature like Hubble is. It's got to be, out of Earth orbit, got to be out where it's doesn't see the warm Earth at all. So we're out at the L2 spot, a million miles away from the Earth. And it's got a huge deployable sunshade that's the size of a tennis court. And yet it's only half the mass of Hubble. So that's part of the equation, is how do you get this thing into a rocket and launch it with any reasonable chance of having a mass that's anywhere near what you can launch. This does not seem to want to look big. I mean, no, it does. Okay, so I'm not going to go through all these, but these are the technologies that were all developed for JWST. I am going to talk about the beryllium mirrors. I figured I picked things that you guys are interested in. So mirrors, yeah, that's certainly the case. The aerial density of these mirrors is less than Hubble. It's about, the JWST mirrors are about 20 kilograms each one, which is about that big around. The mirror itself, all the stuff that we put on the back of it, which you'll see shortly, which ends up totaling about 40 kilograms. So they're lightweight, again, about 3 times the aerial density of what Hubble is. The composite structure, I'm not going to talk about, except for the fact that it's got to be really stable, and we need to know its coefficient of thermal expansion very well, both at room temperature and at cryo temperature too. The ASICs that we developed, it's an integrated circuit that's specifically for mounting on the side of the detectors, that is also cryogenic, that helps get the signals off the detectors down into the to the rest of the electronics. Microshutters, I want to talk about those. That's sort of a microshutters on the ground-based telescopes are big, huge masses of cables and wires and integrated, matrices like this which move around, and they can move rows up and down and rows and columns up and down and expose certain areas of the field, which then is projected onto the detector. This is done cryogenic and in space, and you'll be amazed to see that it's 250,000 little shutters that are all mechanically controlled by a magnetic arm that sweeps over the entire array and sets which shutters are up, which shutters are open, which shutters are closed, which shutters are open, which shutters are closed. And so you can look at 150 objects in the entire field and ignore everything else and take spectra of just those 150, which is amazing. I guess that's the next one. So this is the mirror. This is one of the mirrors. The thing that's interesting about the mirror is these things are in these little cocoons. You know how when you order food at the hotel and the guy comes up and he has the lid that opens up and lifts the thing off the top, and there's your plate of food. Well, that's what all the mirrors were in. All these rings here are all inside of the top of it that they lifted off. All these aluminum canisters that they backfilled with dry nitrogen or evacuated. I can't remember. I think they backfilled them with nitrogen. So this is one of the mirrors out at Goddard, being inspected to make sure it looks okay, that it survived the shipping. We had all these mirrors, all 18 of them, in a stored up above behind where it was taken. And so the next picture. Okay, so this is the back of the, so again, realize this is all at 40 Kelvin in space. On the ground, it's at room temperature, 300 degrees Kelvin. So we have a mirror which has to be shaped for Kelvin, tested at both room temperature and at 40 Kelvin. So how do we adjust it? So on the back of it, first thing we do is we lightweight the entire beryllium mirror. So the back of these beryllium mirrors is all lightweighted. So they're all, a lot of the mass has been taken out of the back of the mirror, so make them lighter. Then there's these wiffle trees that are mounted on the back, which can adjust tip, tilt, and up, down, and also curvature. See these rods here? These rods go off to the center. There's a piston that goes down the middle of the mirror that you can actually change the radius of curvature of that mirror. So you can do that. And of course, the issue is they have to be aligned to 1/10,000th the thickness of a human hair. So these are two-stage actuators. They're proprietary design that, in fact, some of the pictures you may see of JWST, the backside, the images are fuzzed because they don't want you to see what's in underneath these little things. But the two-stage actuators that they have, all operating at 40 Kelvin. So that's an entire assembly. Okay, next, there we go. So then we have to take them and mount them into the backup structure. So there's the composite backup structure. There's the first mirror being lowered in. This is all at Goddard Space Flight Center, being lowered into its position. But it's got if you notice, it's got a black cover on the back of it because we do not want to have to touch the mirror surface at all, which are gold coated. The whole observatory 18 mirrors has got 2 ounces of gold on it, sprayed all over. And of course, why gold? Because it's great for infrared. Next. All right, detectors. So there are 2 sets of detectors on JWST. There's the near infrared detectors, which are basically 0.6 to 2.5 microns. Those are Mercad Telluride detectors that are built by Teledyne. They're each one is, is 2048 by 2048 pixels. There are 4 of those in the NIRCam instrument. The NIRCam instrument, so that's near infrared camera, for those of us that don't want to know what those things all stand for. There's 2 completely redundant NIRCam instruments, and I'll show you what they sandwich together look like. The reason is the camera, the NIRCam instrument, is the critical instrument on JWST. The next most critical instrument is the spectrometer. There's no doubt about that, NIRSpec. So there's NIRCam, which is the camera, NIRSpec, which is the spectrometer. And then there's the mid-infrared camera. So there's one mid-infrared camera that I think I have a picture of on the next slide. So this is the near cam, goes from 0.6 to 5 microns. It's imaging, spectroscopy, and coronagraphy imaging. So here's the Miri detectors. So these are 5 to 28 microns, and these are arsenic dope silicon, 1,000 by 1,000 pixels. Just one of those. We just have one of those, which is used for both, again, imaging, spectroscopy, and coronagraphy. Next. All right, microshutter. So this is what I'm going to not read all these things, but I told you the whole idea is, here's the image of the field, a crowded field, lots of stuff. We don't need to take spectra of everything. I want to look at that galaxy, that spot, and that spot. So I command the microshutter array to only open those shutters. The rest of them all stay closed. So then the camera only does spectra for those spots on the detector. The rest of them we don't care about it for this particular image. So it's the first electromechanical device used in space for science. They're very small. The next slide. So here's how big they are. This is how big. There's the printed circuit board that they're on. This is the entire array of 250,000 detectors. This is a scale. So you can see the scale here. It goes from, I can't remember what this is, 300 micrometers down to whatever the scale is here. I think that's 1 micron. So there's the size of human hair. So that's how big these shutters are. Right? They're not big at all. And if you can think about, you run over the top, which is the flip side of this, a magnetic wand, basically, that I can program which one of these arrays opens and which one stays closed. And this was a technology which took us, we thought we had it done, and then we ran into problems. We found out that we took them down to temperature and cycle them back and forth to room temperature. The actual shutter itself would potato chip, so it would get hung up on the edges. And so we had all sorts of problems with these. They don't all work. Of the 250,000, a few percent weren't working before we even launched. But the requirement was not to have them 100% working. It was to have 90 or 80%, whatever that number was. So we met the requirement. Next. All right. So the sunshade, made in the shade. So again, we have 5 separate layers of very thin material. This is Kapton. It's about half the thickness of a sheet of paper, each one, coated on different sides, depending upon whether it's on the sun side or it's on the cold side at -400 Fahrenheit. But this is the size of a tennis court, and you'll see the picture shortly. They have to be separated. So they have to be, so again, this is at room temperature down in Huntsville, Alabama, the company that made these. So you stretch it out in 1 gravity. You go, okay, that's great. It doesn't work in 1 gravity. We got to work in 0G. How do we do that? We take it and we flip it over and put gravity the other direction, and then measure how it changed and deformed. One's got to read this way versus gravity the other way, okay? And then modeled it, and then and all you guys who are sailors, we have catenaries and stringers and all sorts of stuff around each one of these layers. So when you separate it and tension it, it ends up being the right shape and separated. So this about that much from each layer. We need 5 to be able to get the thermal gradient. This is for your equivalent sun protection factor. So your SPF of sunscreen, we're at 1 million. So it's good, but it's also there because we need 5 layers for the thermal control or for the thermal isolation. But also we need at least 3 for micrometeoroids. There's another problem. We have and I've got a lot to talk about micrometeoroids. Next. Here is the NIRCam instrument. Both, notice it's symmetric. They're mounted two sides. I mean, there's two identical cameras, one mounted on either side of the other. We take that instrument and we put it inside over here, which is the NIRCam, MIRI, and the fine sensor, which is called NIRAS, which is another acronym. They're all put together. Here's NIRCam installed into the structure. And of course, once we get all the instruments into the structure, we have to have a new acronym. So this is now called the ISIM, which is the Integrated Science Instrument Module. Next. So here's the team, you know, they're all in their bunny suits at Goddard Space Flight Center with all the instruments mounted into, and you can't even see NIRCam because it's down in the middle, all mounted into the ISIM. Next one. And here we are dropping it into the back of the telescope. So this is sort of a strange picture to look at. Here's the ISIM, the instruments all up here being lowered down. Here's all the mirrors. So there's the 18 mirrors pointed down. So we have to move thing all over the place, up, down, left, right, in order to get all this stuff in. In fact, there's the focal area where the beam comes in after it hits the secondary mirror, down into the focal point area, down through that baffle, into the area where the ISIM ends up being housed. Next. All right, so as I said, we do a lot of moving in this thing. So the other thing that's interesting is this telescope, you know, it's 6.5 meters, is too big to fit into any launch vehicle, period, that's been built so far and launched, except maybe the new XLS, but it's not available for things yet. So we had to fold the wings. So we have 3 mirrors on either side that are on hinges. And they have to, again, operate. Now this ends up operating at room temperature because all these deployments, including the sunshade, happens pretty fast, is what we call, you've all seen the Mars stuff. So the Mars, you know, 7 minutes, I think it's 7 minutes of craziness or insanity or whatever, where they don't know what's happening as soon as they're going in to land on Mars and they have no clue. It's got 7 months of terror. That's what they call it. Well, we have 28 days of horror on JWST. But we have to move this thing around. This is all at Goddard. You can see the huge wall of HEPA filters to keep this a clean room, and everybody's in their bunny suits wandering around. We have a rotating thing that we can move it, tip it over, up and down. We have area place to place. Next. All right, so let's see if you can get this thing to turn on. If you get your cursor up into this, there you go, and just start that. So this, so this is the vibration testing of the entire telescope and the instruments. This is all 3 axes. So we got to get it into space. So we got to get it up on the launch vehicle, which has tremendous vibration and acoustics. So this is the vibration, and you can see it dampening because it goes across frequencies and amplitudes. And then we do that axis. We do all 3 axes. They'll switch over the other axis and look straight down at the top. This is all designed to fit the profile of the launch vehicle that we have, Ariane 5. So, you know, shake your telescope and see what happens after you do that. Now, the level that we're shaking it at is 3 dB above what the environment should be on the launch vehicle, because we got to make sure it works. So it's all cranked up a little bit. Some of the subsystems that are inside of this have also been tested, same sort of level. So what we try to do is at each successive level of integration, things that have already been tested at a lower subsystem level, we don't have to retest at that higher level. So we again sort of back it off and notch it around. We had to notch the filters of the frequency response to get around the microshutters. The microshutters were a problem. We had to get Arianespace to accept those notches where we would not vibrate at certain frequencies, that they would accept that, and they could guarantee that they wouldn't give us that problem launching. This is the acoustic chamber. So we put this whole thing inside of a big chamber and put sound waves all over it, blast it like mad with sound. So this completes all of the room temperature testing of the telescope and the instruments. This is the final testing that we did at Goddard. So that worked great, thanks. So next slide, so we took it to Johnson Space Flight Center. So this is the world's largest cryogenic thermal vacuum chamber. It was not cryogenic until I spent $110 million to, literally, I had to carve that out of various places, but anyway, Senator Mikulski helped on that. In fact, she was very helpful at getting some specific money early on for this. So we modified the chamber. It was designed to test Apollo astronauts in. It was entirely designed to stick astronauts inside of it, have them in a pressurized area, and then evacuate the rest, make it look like deep space as best as possible, but so they could get out if they needed to pretty quick. Well, we took the chamber and made it so it's cryogenic. So it goes down to 25 Kelvin. The chamber door, which is, you can see the hinge over here. Next slide. So here's JWST, full telescope, mirrors, all the mirrors are out. Secondary mirrors deployed on the feed legs. See the 3 feed legs, 2 of which stay solid, rigid all the time. This one has a hinge in the middle of it. So that bolt pulls its way out and the secondary mirror comes down this way to go into launch configuration. So this is getting the telescope into that chamber before we close the door. We spent 90 days cooling this thing down, running tests, turning everything on. All the instruments worked. The telescope mirrors all worked. We adjusted them all. We did all that stuff. Oh, and in the middle of that, Hurricane Harvey hit Houston. So there were literally, I have pictures of, there were literally days when the guys at the control center at tables inside controlling this thing from the outside had plastic tarps over the top of the electronics, their manual, the consoles they were sitting at. It was raining in from the ceiling. We actually came within 3 days of running out of liquid nitrogen. Fortunately, we found a different supplier. Okay, so this is video. So if you can click on now, this is going to be, I turned the volume down on this, but click on that. So rather than showing you a bunch of still pictures, there's a great video that they put together. This is about 2.5 years worth, all in rapid speed, time-lapse photography, moving the telescope over. Here's the sunshade all folded up. There we are, putting the telescope down onto the middle section. There's all the sunshade all folded up. It's all fan folded in.
I'm not seeing it here.
You see all these guys running around like mad. So
We've
here's
lost the
pulling
video.
the sunshade out. There we are, tensioning it. So there's the final fully assembled, the wings aren't out, but fully assembled sunshade and telescope. And underneath, there's the backside. So you can see the backside where all the instruments are all buried inside of that. The backside underneath the sun shield is where the spacecraft is. So where all the communications to ground, the high gain antenna, the gimbaled high gain antenna, the solar array that comes out to the side, all that stuff is down under. So that's on the hot side of the sunshade. Everything from here up is cold. This must be the next video. So
We're not seeing any of this.
we can skip that. Go back to the slides. Yes, you're doing a great job. Next slide. All right, so these, I just have some pictures in here that I got, but you know, it's a big thing. I mean, there's a tennis court and there's the little guy standing in the middle of it. And there's the little guy. So again, they have to be tensioned. So we got to tension this thing. They've got to stay separated and work at 0 B. And from 400 Kelvin, 400 Fahrenheit on this side to 40 Kelvin on this side. Okay, next. And then that's, so this is an interesting picture because it shows before we dropped it down, we have to fan fold in And that's a proprietary thing that Northrop Grumman has, so I can't show it. But they fan fold it all in, and then they have a whole bunch of little ties that hold this all together. Hold this all together, that once we get on orbit, all have to be released. So we have, I forget, it's 170 non-explosive actuators across this thing. All of them have to work, and it all has to work remotely. You can't do it any other way. Next picture. That's just a cool picture. Next. So here we are all folded up. So you can't see it, but the spacecraft is all down here. The solar array is all, it's got, I think, 4 or 5 panels on it that's all folded in on the one side. The high gain antenna is all packed up in and close. The two halves, the two sides of the sunshade that were the two pallets, this pallet and that pallet, have been folded up to the top, and you can barely see. These are some of the side mirrors that are on the hinges. The rest of the telescope is all buried in here. There's a secondary mirror. Okay, way up at the top. Next. This picture I love, because we actually have to take this is before we went and did everything we put it back on the top, because you can't put the telescope on top of the state in the spacecraft with it in any other position than straight overhead. So we're sitting straight overhead on a crane for months during earthquake season. Yes.
I don't want to start a long question, but I missed something. Spacecraft. What part are you referring to?
So yeah, so the spacecraft is I don't think I have a great picture of space. So the spacecraft is all below. Go back. Maybe I can go back one.
Let me see if that's possible.
Well, I can try it. That's all right. So the spacecraft, so we have the sun shield, okay, hot on one side, always pointing to the sun. Down underneath there is where the electronics are for all the data processing of all the instruments, all the control electronics that run all the instruments, the command and telemetry processor system, the traveling wave tubes, the amplifiers, and the high gain antenna and a low gain antenna, star trackers, sun trackers. That's what I'm calling on the spacecraft side, and the thrusters. So we have thrusters on the bottom side to maintain the orbit in L2, and to bigger ones, and then the small, they're all hydrazine propellant. The biprops, the larger ones, are hydrazine and an oxidizer, and they maintain the orbit around the L2 spot. So every once in a while we have to maintain this huge, it's a 1.5 million on on the one axis orbit around the L2. So you can't just sit at L2. You've got to orbit all the time and constantly maintain that. And then there's smaller thrusters that are just hydrazine, which we use for attitude control. So when we do slew and some of the fine, we also have reaction wheels. So we have gyroscopes on and reaction wheels. The reaction wheels we use to do the very fine tuning. But those reaction wheels, we spin them up. But when you spin them up, they put a torque into the observatory. So you have to use the thrusters to compensate for the torque that you do. And then every once in a while, as you wind those, you use those reaction wheels, you basically brake them like a bike. You brake them and the car goes this way or the telescope goes that way. And so sooner or later you get down where you're spinning back up again. So now you need the thrusters to be motion of the observatory. So and we have one part at the back end of the observatory, which is a flap, which is a momentum flap to try and from the sun on this entire observatory. So it's not simple. There's no doubt about that. So let's go back one. No, you can't go back one.
I anticipated. Sorry.
You can't go back one.
Empty that remote for a second. No reason it shouldn't be working.
Probably works closer to the computer. There you go. No, that's the other way. There you go. So you can control. No, I need the zoom. I need the dot. Okay, so next one forward. Okay, so here we are. Again, this tips on its side. So before we mounted this thing all on top of the sunshade and the spacecraft underneath it, we had to tip it over. And for the first time, and I think it was in 2 years or 2.5 years, we had to tip it on it completely on its side and walk the secondary mirror out. Because we have to hang, stringers from the ceiling, because we got to offload everything. None of this stuff is designed to operate in 1G, period. So all the mechanisms, all the motors, all the drive mechanisms are designed for 0G, not 1G. And so when you try to walk this secondary mirror out and make sure that that one hinge that's back on the other side expands properly and locks in place, and the secondary mirror is in the right way out here in front of the telescope, we have to do that all by pulleys and hands and people walking around and all sorts of stuff. So anyway, we took that telescope, tested that it was fine, put it on top, put the whole thing together, and then a container. So this is the telescope being inside, huge container that we then wheeled out of Northrop Grumman, drove it off to the port in LA, put it on a barge or a ship. This is actually a ship that the Ariane Space, the French company that builds the Ariane 5 rockets, uses all the time to get their rockets from France to French Guiana. This is it coming into French Guiana. This is the container coming off. And of course we had, pressure sensors on this, altimeters on the, not altimeters, pressure transducers on this thing, looking for accelerometer on it, for looking for motions and temperatures and all that sort of stuff. And the whole thing was backfilled with evacuated. I guess it was evacuated or backfilled with nitrogen. I can't remember which anymore, to get it all down to French Guiana, which is where we launched from. Next. Here it is. Here's the beast. So you can sort of see right there is the spacecraft. Underneath the sunshade, down here is the entire spacecraft mounted to an adapter ring on the very top of the Ariane 5 rocket. This is the shroud coming down over the top. They put the two halves together, bring it down over the top very carefully. This is after we loaded the hydrazine into the tank, which is in a different facility. Hold it down, and everything sort of went well. Next.
For the benefit of the people online, could you very briefly and sparingly tell us what you're pointing at when you're pointing?
Oh, okay, sure. So what I'm pointing at now is I'm pointing at, that's right, I can't see the pointer. So on December 25th, 2021, we launched it on the Ariane. This top picture on the left, top right side is the picture, the last picture. So the Ariane actually had on as a tech demo a camera. It's the first time they ever had a camera looking forward top of the Ariane rocket after you get rid of the payload fairings, after they separated and went and fell away. That a camera on as a tech demo, which was great. So this is JWST. So there's your answer. There's the spacecraft. I mean, that's all you can see from this side is the bottom of the spacecraft. And that ring is the adapter ring that connects it to the top of the Ariane second stage. Yeah, right. That's a great picture. And then we're all waiting for the solar arrays to deploy. I had numbers of discussions with the fact that you build these things, the thing you think about is going to work, and as you've done a zillion times before, and it's going to work with no problems at all, is always where the problem. The stuff that you never know that you've done before, you spend all your time working on trying to get it right. And so we ended up having lots of problems with the hinges on that solar, believe it or not. We finally got it all fixed. But we were sitting there, I'm sitting there watching this down in Beverly with my grandkids, who, by the way, they were allowed to open, this is Christmas morning, they were allowed to open their stockings, not any of the presents, until after we watched JWST launch. So this was sort of a surprise, because I'm going, geez, what? Not so early. So it turns out they weren't early, they were exactly as it was scripted to be. But it turns out that it was good. It was when they were, because we could actually see this and we have a video of this as the rocket, as the JWST goes away from the rocket, of the solar panels deployed. We get positive power, power's there, and everything's working great. Next. All right, where are we? So here's the sun, point sun. There's the Earth, there's the moon. We're 4 times away from the Earth than the moon is at L2. So we're in this funny halo orbit that has to keep the one side always pointed to the sun. And we have to have our high-gain antenna always pointing to the Earth while we're doing observing, because we're doing about 12 hours a day, a minimum of 8 hours a day of downlink from the spacecraft to the Deep Space Network to get all the science data down and the engineering data down. And so we're pointing, the only time we don't run the gimbal at the time we're trying to take very specific observations. So we try to only move the gimbal on the high gain antenna when we're doing slews. So that's sort of orientation. Next. So I put this together, this again, you can't really see the spacecraft because it's down buried underneath, but 140 release devices. So these are all these little things that have to release to spring this thing out and be able to string it up. There's something like a total of 1,300 in all this thing, 400 pulleys. I mean, because, you know, all this stuff has got to be spread out and pulled out. There's no astronauts up doing this stuff. We're at L2. So this is all done from commands from the ground and then done all by itself in very precise steps. And then they stop and we analyze stuff and say, okay, let's go on to the next step. When we deployed it, there were some on the inner part of each of these 2 trays that held the sunshade. There was the very last one at the end. We have a reed twitch, which should have shown that it had been released properly, and it wasn't. So we're in panic mode for a day until we realized, look, it looks like it's probably good. Just go ahead and beat the rest of the sun deployment, and it all worked. So lots of pulleys, lots of cables, lots of testing. We tested this thing. We deployed the sunshade, the full flight sunshade 3 complete times. The telescope. Oh, one other little thing is the cryocooler for the MIRI instrument, which runs at 6 Kelvin, is housed way up here by the detector in the backside of the instrument module. That's where the Jules Thompson coolers are. But there's a slinky that runs all the way down the back of this thing, down into the bottom. It goes down through the sunshade, down into the spacecraft at the bottom, where the 2 pulse tube coolers are. It take it down to 18 Kelvin. So we have a slinky that's in here, and this whole structure to get away from the sunshade, because it's still, you know, it's still got some heat, even in the inner side versus the outer side. This whole structure telescopes up 4 to 6 feet. So when we get up into space, one of the first things we do is we telescope that up. The slinky runs up. We turn on get the cryocooler turned on after we get the sunshade deployed. But again, that's 28 days. It's to that 28, it's the edge, on the edge, as we call it. There's a great video link that talks all about that. Next. All right, so you take your telescopes and you go outside and you go, okay, Azelle mount, and or it's a equatorial mount, whatever it is. We're not so lucky. So here's the telescope. We can't move the telescope relative to the rest of the observatory. The spacecraft, there you see the spacecraft solar array on that side and the sunshade. We cannot move the telescope separate from everything else. So we're limited to 360 degrees of roll about that axis, okay? We're limited to 50 degrees of motion about this axis, the telescope pointing direction, because if we get too close this way, the sun comes over the top of this edge here, and we'll start to see some of the secondary mirror. If we go too far past 135 on this direction, the sun comes down over this side of this side of the telescope. So we're really constrained by 2 things. One is we stay pointed at the sun all the time. You can rotate 360 this way. You're limited to 50 degrees of motion this way. And the rest of it is up to somewhere, wherever your targets are in a year's period of time. because you can't look at everything all at the same place. We can't look at anything inward of Mars. I mean, we can look at some asteroids and Mars, but we can't look. We looked at DART. We did take images of DART, but you can't look at Venus. You can't look at the sun. You can't look at comets when they come inside the Earth's orbit. Next. All right, so this is the big final picture. So this is a picture of Hubble on the left, Hubble ultra deep field picture. They're both about the same size on the sky, about 2 by 2 arc minutes. There's 5,000 galaxies in this picture. And this is a visible infrared, a micron, 1 to 2 micron Hubble. Took 25.5 days to get that image. Okay, JWST. Well, we set a bunch of science to go do, not real science, but go off and show the capabilities of JWST. Spectroscopy, different operating modes for all the instruments to show the capability that we had. So this was what we call the ERO, which is the release observations. This was all done leading up to June of 2022, last summer. So just to show the demonstration, not to do any real science. So here's an image of a similar field of an area. This is actually a gravitational lensing system here. These, you see some really neat arcs around here every once in a while that are gravitationally lensed galaxies that are even further away than you can see them. It also has some very, very faint galaxies in it, which are these little faint things here and there. Again, galaxies. This was only 12 hours of observing. Actually, it's even faster than that because it's 2 hours per each of 6 filters. So you can see the power of this thing. This is just, it's a powerful tool. There's no doubt about it. Next. All right. So I wanted to show this only because down at the very bottom, you see the near cam filter wavelengths. These are all, if you multiply by 100, it's all in microns. Other than that, I can't read these. But the bottom line is this is how we make pictures. Everything comes down. It's black and white. It's all just, it's ones and zeros. We go through a bunch of algorithms that we've used for Hubble as well as for JWST. The NearCam instrument, the way they pick the colors is to basically go by the wavelength. So the very short wavelength, the very short end is in the very blue, and the very long wavelength, in this case would be 5 microns, is the red. And then they tweak these colors a little bit and play with them and do whatever things. And then you get to see, some terrible things that are stars. We don't like stars in these pictures, but so one interesting thing is see the diffraction pattern for that. It's very unique for JWST. You don't see that for most any other telescopes because it's a combination of the 3 struts that hold the secondary mirror plus the shape of the main telescope. It's a hexagonal shape, and that shape combined with the struts gives you all those spikes that you see on the diffraction image for a star image. So so I go, okay, what's this? This is mid-infrared. So this is the mid-infrared image. Well, again, rather than going and picking with the very red end of the spectrum and starting from there, which is 5 microns, and going out to 28, which is where the mid-infrared instrument goes to, they go back and start all over again. So the mid-infrared instrument starts at its shortest wavelength in the violet and go its longest wavelength at 28 microns in the red. So you don't get an image that looks anything like what you'd expect a visual picture to look like. Whereas the near infrared is much closer to what you sort of expect to see. So when you see the near infrared, you go, oh, that's a bunch of garbage. It looks like, somebody with a crayon. My grandkid did that with a crayon. But that's part of the problem. This is that they basically did the convention that said, hey, look, it's a separate instrument. We're going to go, the standard convention is the bluest is the shortest wavelength and the red is the longest wavelength. So that's why the mid-infrared always looks a little funny. Next. All right, so here I had to show some spectra. So this is a section of that same image, and this is 13.1 billion year old galaxy, which not only can we get an image of it, I mean, it's only after, a few hours, but you can get the spectrum of it. So there's neon, oxygen, hydrogen, you name it. And you can just see the lines just popping up all over the place. So that just shows the power of doing imaging and spectroscopy at the same time. Next. And this is another one. Again, this is another technique. Rather than looking at emission lines, you can look for the Lyman alpha break, which is at 912 angstroms. Anything shorter wavelength than 912 angstroms is completely absorbed by all the neutral nitrogen gas in that galaxy, in that area, just a neutral gas. And so you see a very sharp edge to where the Lyman alpha break is what they call it, and a very sharp decline in the emission. And so that then go back and use Hubble's constant and Hubble's loop and figure out, what Doppler shift that is, and therefore what it is distance-wise from the Earth. This one is, these are all different Z factors here, but Z of 13 is roughly 330 million years after the Big Bang started. So it goes back. So the power of this is just amazing, just unbelievable. And we have dual observing modes, so you can observe parallel. So you can use one camera, near cam, and near spec at the same time. So you don't have to do it sequentially if you don't want to. Next. I had to put in some some exoplanet stuff. So again, this is one of the images they had of what is it, WASP 39b, which is one of the exoplanets. It's rich with potassium, water, carbon monoxide, sulfur dioxide, carbon dioxide, all those great things. But there's the spectra. I mean, these things just pop out. The Hubble Ultra Deep Field, the one that I showed that was comparison to it, was 12 hours. They're going off, I think, this summer to stare at a blank space. Again, there's no such thing as blank space. Everything you look at that's the size of, a grain of rice held out at your arm is got, galaxies in it, no matter where you look in space. So they'll go back and look either at the North Galactic Pole area or the South Galactic Pole area, get rid of all the garbage that's in our galaxy, all the clouds and all the stars, and sit there for 100 hours. Next. All right, so on-orbit performance. So a little bit of this is thermal stability is amazing. I mean, the temperatures move around depending upon how they're fluing and our targets are going to. But when they get settled down, the measurements are within the noise error of the measurement thermistors that they have on board. Same thing with the instruments. Pointing, 1/10 of an arc second is typically what the pointing is. Our pre-launch prediction was 0.014 arc seconds. The requirement was to be at 1 arc second. So we are 10 times better than what we're required to be at. Pointing stability is 1 milliarc second. Spec is 4 milliarc seconds. The stability is really good. The wavefront error, so this is where we get micrometeoroids. Wavefront error. The wavefront error right now is 61 nanometers. It's still 2.5 times better than what we expect at. So about 10 nanometers of that wavefront error is due to micrometeoroids. One impact, a big one that we had early on, it's sort of, we didn't expect to see anything this big, contributed 9 nanometers. That was after correction. Before we corrected it with all those wiffles on the back of the mirrors, this was in the edge of one of the mirrors, which is also a bad place to be. But with all that adjustment of all the mirrors and the adjacent mirrors around it, we went from 32 nanometer wavefront error down to 9. Significant improvement. And we're at about 10 now. We continue to monitor that. We get about 1 micrometeor hit every couple of weeks, 1 every 2.5 weeks, sort of. We haven't had any big ones. Good. But every 2.5 weeks or so, we get another one. Every 2 days, we go off and measure the wavefront error, and we decide, is it okay where it is? Every couple of weeks, we do an adjustment. We make adjustments to the mirror surfaces if we need to. So all those mirrors can be adjusted. Big difference from Hubble. Hubble, one big piece of glass that was figured wrong. I can tell stories about that one. Observing efficiency. So 83% of the time, this is actually from last month's monthly, is the 83% of the time that were required for visit execution. So that's guide star, find where your guide star is, go look at your guide star. Target acquisition to your target, wherever you have to go to get your target from the guide star, calibration, all that kind of stuff, and the actual visit time to do the science. That's 83%. 15% of the time is slewing around, and the rest of it is sort of just little bits here and there, not a lot. So very efficient. This mission is a 5-year mission. We had Arianespace did an amazing job launching us, and they put us on such a good orientation that we didn't need to use any of that hydrazine to be able to adjust the position as we went out to L2. Going out to L2 is a little tricky because if you fire your engines and you overshoot L2, you can't come back. There's no way to turn this thing around and fire the engine in the other direction. So you got to be really careful that you incrementally get closer and closer to it, but never going past it. So they did such a good time. Good job. Of propellant. So we all know what's going to happen. The instruments are going to fail before the telescope, before the propulsion system runs out. So science, where we are with science. Cycle 2, which starts this summer. We put out an annual call for scientists to propose what kind of science you want to observe, which instruments you want to use, how much time do you think you need, where your targets are. We have double-blind review teams that go off and look at those proposals, so they don't know the name of the author who's proposing. This is part of the double-blind to get and make sure you don't bias yourself to the old scientists that have been, all the gray beards that have been around for a long time. Institute does all that, and they come up with a ranking of which ones are the highest priority. We had 5,000 hours available for the GO, which is guaranteed observers, and we had 36,000 requested. So that tells you the demand for this telescope. The second cycle, first cycle will be up sometime this summer sometime. 1,500 proposals, 52 countries, 46 US states plus DC, Puerto Rico, and US Virgin Islands. The Europeans had 33% of the time. The Canadians got 3.4. Technically, they're guaranteed 15%, I think, 20% of the time of observing as part of 15% contribution to building JWST. Built the entire detectors and the not the NIRCam, the near spec instrument, except for those microshutters. We provided the microshutters and the detectors, and the Canadians provided the fine guidance. They have that guaranteed amount of time, but no one has ever, even for Hubble, has ever gone back and insisted, I need to get my X amount of time, because they rely on their scientists in their community in Europe for all the member states to put in good proposals. I mean, the bottom line is they should be doing the stuff that's the highest science priority. So that's where we are. So that's where JWST is right now. Was it worth it? I don't know, $9 billion, 25 years to build, 20,000 people worked on this from over 14 different countries. So as I said, I've been working on this thing since 98. Working on it a little bit. So questions? Any burning questions? I can answer anything you want. Yes. Yes.
I saw a picture of Hubble early in the presentation.
Yes.
That's something
Right. So could you go back to the very beginning picture? You think you can do that? Here, you can do the remote. Yeah, so there's a good story there. I told them this story, so I'll go back and tell it. There's lots of interesting stories on this thing. Of course, I'm going to make you go to the one just beyond the very end at some point. but that's all right. So the reason I picked this picture is because this little white thing here on the back end. So there's a story. John Grunsfeld was one of the astronauts who was on this, along with several others. John, I ended up working for when he came to headquarters after he retired from the astronaut corps. He was the head of the science directorate. And he and I used to joke about this picture all the time, because the issue is when they deployed Hubble for the very last time it will ever be serviced by astronauts, they saw that. They go, oh, geez, there is a styrofoam, or it's a plastic cup that they put on to cover an antenna that they didn't want the astronauts to rub up against and be able to rip their astronaut suits. And so they left it on, and then as it goes away into space, they go, oh, geez, we forgot to take that stupid cup off. So I always know that that's the last servicing mission. Yeah, right. Yeah, right. Well, John Gunsfeld and I made several jokes about that for several different times. So if you go all the way to the other end, yeah, it won't take that long. So funny stories. Yeah, right. So I told you the one about the water and Hurricane Harvey. We had some interesting problems with the hinges, as you would expect. We had lots of problems with the sunshade. The sunshade, we developed a criteria that said we're going to deploy. So this is deployed in a clean room in Northrop Grumman, and it's at room temperature. And the deployment is all done manually. I mean, you can't turn the pulleys on and get them to push the motors to push it out, because they're all designed to work at 0G. Everything is loaded for 0G. We don't want to put in enough weight and mass into the drive motors to drive everything in 1G. That's just waste of mass, and we don't want to waste mass trying to launch stuff. So as a result, everything's got to be done by hand. So all those mechanisms to pull that, you sort of saw it when we did the video. They're all pulling stuff out, and they're moving a little bit at a time, and they're pulling stuff out, and they're pulling stuff out, whatever. And they get it all out there. And we had to do that 3 successive times with no failures before we said we're ready for launch. So we did that twice, packaged it all up, and then we had to take the whole vehicle, spacecraft, sunshade, telescope, instruments, the whole stack, fold up the two pallets, and take it over to another facility into a vacuum chamber, not a thermal vacuum chamber, so we didn't take it down to temperature, but just into the vacuum chamber to run acoustics on the entire observatory, much the way you saw us do for the telescope and the instruments. Not at that same level, but a next level down a little bit. And they vibrated it all, shook it all. They said, oh, worked great. They take it out, they take off the cover off the top of the observatory, and they notice there's 440 size screws, nuts, and washers on the floor. And these are short 440 screws. And I think there was a total of 40 out of 1,000. And so the issue is we held it all over. And so the problem was that the sunshade, we fold everything back up into the 2 pallets. All the sunshades come into the 2 pallets. You tie them down. There's a cover that comes over that flips over the 2 sides. If I look at the pallet this way, there's a cover that comes over either side, which keeps the sunshade protected during launch, because we don't want it vibrating back and forth during launch. So these covers come over, and they're, again, tied down. They're all non-explosive actuators that have to release these little release mechanisms, so they spring back and over. Okay, so the little springs that they use to roll them over are tied on with 440 screws and nuts and washers. These were done in Huntsville. The drawing did not specify, because it's standard engineering practice, that you always have 1.5 threads showing after you put your nut on the top of a screw. Everybody knows that, right? It wasn't spelled out in the drawing. Northrop didn't spell it out. The guys down in Huntsville, don't ask me why. It was never spelled out in the drawing. That's not an excuse. Standard engineering practice is you always have 1.5 threads showing. They didn't have enough threads showing. And so some of these things backed off. That set us back 2 years, right there. So this mission at peak, I'm spending $1 million a day on this project. $370 million a year on this project. When I came on as director in 2010, it was several $1 million behind. It was several years behind schedule. And the administrator and the head of science and the deputy chief administrator came to me. I'd been up in the chief engineer's office building as the deputy chief technologist, starting a whole new technology center for the whole agency. And they came and said, Rick, come down here. Can you fix JWST? So I said, yeah, sure. What do you want me to do? So $3 billion later, 4 years slip of the launch date, I had to convince the White House, the OMB, Office of Management Budget. I had to convince NASA headquarters. I had people at NASA headquarters that said we should cancel this thing. I had to convince the science community it was still worth doing. And I had to convince Congress that we weren't going to ask for any new money. We would take all the money out of existing NASA budget. They all agreed to that. And so they all approved it. And the good thing is for 7 years after that, we stayed on track. We didn't need a penny more until all those screws came out. So it was, so that was again, one of these things you think it's just a simple thing. You just put these flaps on and put these little retainers in and just screw them down. So the other thing that we learned is that most of these big space missions don't have the kind of what we call soft hardware that we had on this. Soft hardware is the sunshade. It's all the mechanisms to deploy that stuff. It's all that we have frill, we're going to call it that, around the edge of all the mirrors. There's a little bit of frill that we have to keep blocking out heat, basically, that's coming into, we don't want into the telescope or images from other things coming in. We do have some funny little arcs and things like that in some of the camera images, which are multiple bounces off the secondary feed legs into the cone in the middle of the telescope, bounced off something else and into one of the detectors. And if you look at a certain position in the sky and have a certain bright star over here, you'll get an arc or you'll get a glint or whatever it is. So we've had to work a few things like that. So next slide. So there's the sprites. So so there's another great story. If you got a few minutes, I can tell you this story. Back in 93, I was up until 90 through 95, so 88 to 95. I was in the heliophysics division. I wasn't in the astrophysics division. I was in the heliophysics division. And I had a bunch of stuff I was working on, future missions that were flying, that we flew. But the program scientist, one of the program scientists came to me one day and said, so, the guys at Alaska, University of Alaska, who were on the combined release and radiation effects satellite, which I was in charge of, which are all low light level auroral people. These are all guys that have been doing auroral studies forever from University of Alaska from the ground. They came and they said, we got time to be as a secondary payload on the NASA 990 to fly, or DC, I can't remember which one it was. I think it was the 990 to fly. No, it was the DC-8 to fly as a secondary payload on a mission that was going down and flying around thunderstorms in Florida. And this was an earth science experiment to do thunderstorm measurements and lightning and all that cool stuff. So we got to be a secondary payload on that. But, they don't want us flying at night. They want to look at thunderstorms and stuff during the daytime. So they didn't get any data at all. They had, 1 or 2 nights down in Florida and they didn't get anything at all. They come back to, plane goes back to Ames Research Center in California. DC-8 goes back there. And they call up Mary Malott, my scientist, and they go, here's what we really need. We need a dedicated flight of the DC-8 to fly over the Midwest. And there's 3 nights we can do it this summer. And we want a dedicated to fly our all-sky camera in the dome of the DC-8 and look for sprites. And so Mary came to me and goes, they just want, one chance to do this. They'll just take the plane out of Ames and they'll fly it over the Midwest when the thunderstorms are really going to look like they're going to be miserable, and fly over the tops of thunderstorms. And I just, I need $10,000. I said, I got $10,000. So I basically transferred the money to her. She put it on a grant that they had with the university for other stuff that they were doing. And you can always modify an existing grant to the tune of like 10 or 15% with nobody asking any questions. So we did that. And so they went off in 93, and got the first black and white images of sprites with actual altitude data on how high these things went. The following year, they want to do it again. And I was in charge of all the sprite work for the next couple of years. And so we put it on and they did color camera. So this is color image, the very first one that we had a press release on, taken on July 4th, 1994, of a sprite. And you can see a series of a couple of the sprites. There's a few little one ones over here. But this is a sprite with an altitude scale on it. Nobody had altitude scales on these things at all. And then at the same mission and the previous one too, we saw blue jets, and they go, "What the hell are those?" So blue jets. This is a great image that I took off of a video that was taken from the space station. Blue jets are blue, and they look like cones going up from the top of the thunderstorm up, maybe 40 kilometers, 40, 50 kilometers, not super high up, but they're blue. They look like Cherenkov radiation. I mean, they just look like they could be nasty sort of things. And you can actually see them propagate up. I mean, they're slow enough to do that. These things, you blink and you'll miss it. So you just can't watch and go, "Oh yeah, there's one," and you see it and it goes up. These you blink and you miss it because it's one frame of these cameras. The blue jets, however, they're only around the most energetic thunderstorms, ones that have baseball-sized hail falling out of them. At the top, when you get this discharge, and again, the sprites are the same thing. You get a lightning bolt going down to the ground. There's a discontinuity between the electrical field at the top of the cloud and the ionosphere, and that's when these things take off. And the same sort of things happens here, although this one, there's actually an elf up here that appears before it. So elves are, you can't see it in this picture, but elves are big rings of things. In fact, if you see it, you see the elf form first, and then this blue jet comes up from the top of the cloud, right from the top of the thunderstorm. So these things go off, and so I'm in charge of this stuff at NASA headquarters. And I see that, and I'm working with the University of Alaska folks, the scientists there, and they're doing stuff. And we did 93, 94, 95. We went down to South America and showed that these sprites are not just in the US, they're all over the world. And we started to understand a little bit about what these blue jets were. And so I went up to the deputy associate administrator for the human spaceflight system. And I said, "I don't want to be alarming. I don't want to, raise any flags, but we have reports of U-2 pilots in Vietnam seeing a blue bubble come up underneath them and just, wing to wing glowing of the U-2 airplane. So these things may have some energy in them. Probably do. We don't know. Don't have because U-2s were all fly by wire. So there weren't electronics, anything anywhere in these things. So I said, "I'm not sure you want to have a shuttle landing over a thunderstorm that's super active as it's coming in to land in Florida." So he said, "Yeah, that's a good idea." So they changed the landing pattern for the shuttles, not the pattern, but just if there's really active thunderstorms in the flight path when you're coming in down into that 20, 30 kilometer range, go around. Probably get it next time. So you guys said something about sprites, so I figured I'd put this up just for the heck of it.
Were the existence of these things contested before you did this?
So there's been sort of anecdotal story for years. The Indians in Peru along the coast would claim that they would see these things, sprites, up over the tops of the mountains looking east. You gotta have conditions where you can see stars, first of all. So when we flew in 94 and 95, when we flew, can't tell anybody this, but we turned all the lights off on the airplane, all the navigation lights on the airplane off, because we need low light visibility stuff. So they just turned the lights on, and we're flying around with no lights on at all. Lightning's going off and on, sprites are going up and down, blue jets are going all over the place. I mean, it's amazing that you can see this stuff. But there was sort of anecdotal reporting. Nobody had, since they're from thunderstorms from the ground, you got to see the thunderstorm over here and stars above it to be able to see anything. And it's a flash of I mean, you blink and you miss it. So you won't see much of this stuff, but you have no idea how far away it really is. So you can't tell the height. So that's why we had the all sky camera on, and they had star fields around so they can get the elevation to the stars. They knew what that all was, and put a scale on it for the first time. So they did that the previous year. This is the first color one that they have. And since then, they've been doing this stuff in the space station. There's a bunch of stuff. They just look at this stuff all the time. And, you know, it doesn't really do much for the overall energy, for the overall electric budget for the globe, but they're there. There's no doubt about it. And these things, the blue jets, you don't want to mess with.
Can you see either of these phenomena from the ground, or is?
Oh, yeah. So the blue jets, no, you probably can't see those from the ground because they're right over the real center, miserable part of it. Usually the backside of this, the backside of the thunderstorm, where you hear all those real boomers. Those big boomers are the big positive strikes, which generate the sprites. So you have a better chance of seeing a sprite if you can see a thunderstorm off in the distance, sort of, or over, not overhead, but and you look for those big boomers, and you can see stars above the thunderstorm. I mean, you got these strange conditions. You guys all know how to do this. You know, you want low light conditions out of the city, you know, that kind of stuff. But you can see those. I think I may have seen one, maybe once. But again, you blink and you miss the whole thing. So,
Is this an electron discharge?
yes, yeah, it is. It's a discharge. Again, it's an imbalance between the top of the cloud, the thunderstorm cloud. When you get a lightning bolt down, it discharges down out of the cloud and leaves the top of the cloud to the ionosphere with a potential difference. And in that potential difference, you can get these accelerating electrons.
It's a cascade of ionized gas?
I don't remember exactly what you're actually seeing. I think you're mainly seeing, if I remember correctly, the sprites are mainly ionized nitrogen gas.
Yeah, okay. Wow. What a great perspective. And thanks for sharing your experience.
Well, it was you guys with your thing that you put out about me when you said, oh, and he says some bright stuff. I thought I'd have at least show a good picture showing. That's when we actually had a headquarters press release on way back that's got my name all over it, I guess.
Yeah, I've been watching this stuff from the chimpanzees all the way to the moon landings and the Hubble and the mistakes. And now watching the Webb, it's like, okay, what a perfect launch and insertion and deployment. And you guys did a marvelous, marvelous job. And how low in vacuum could that cryo chamber go? We used to do -9, but that was in a small chamber. And you guys are doing outer space vacuum.
It was down. It didn't have to be outer space. It just had to be low enough that you could maintain a difference between the nitrogen. They had a nitrogen jacket at 77 degrees Kelvin, an inner helium jacket. It was brought off from helium gas, so it was in the tens-ish, 10, well, not quite 4, but tens-ish or so. But you wanted to get down to 25 Kelvin, so you needed enough of a vacuum to be able to maintain that thermal separation. So I think it was like 10 to the minus 10-ish, 10 to minus 11 maybe.
Yeah, that's good vacuum. You got to be real clean in there.
You got to be really clean. I mean, we had to clean it out, and then on top of that, we had, you could just imagine all the vacuum pumps that we had pumping in that chamber to maintain that vacuum while we're trying to maintain a thermal difference across all those areas too.
Did you do turbo pumps, or will you do star pumps or other types?
There were big turbomolecular pumps.
Yeah, with cold traps or whatever else.
Yes, with all sorts of all that. I mean, there's pumps all around that chamber on all sides. I mean, they just go all the way around.
Wow, a great.
Again, it's a 90 foot high by 55 foot wide pumping station, you know.
Yeah, chambers I'm used to are 5 cubic feet or less, so having the size is phenomenal that you can do that.
And the
Incredible.
vacuum wasn't as much the concern as it was getting enough to be able to maintain that temperature difference. And of course, then you have all the cabling and all the vibration that goes from all the pumps. So you got to isolate all the vibration from all the pumps and all the cabling that goes from the telescope, the mirrors, the instruments, all that cryogenics. And then we had 3 large flat mirrors suspended from the ceiling to be able to get basically far field from the telescope. So we had all that stuff hanging around and all those cables coming out of the vacuum chamber and tied into consoles, on the floor.
It's
So
amazing.
it was, as I said, it was 90 days and many, many years to design all that. All just the testing, let alone the hardware.
It's well worth it.
Yeah, it was, I think it was, but then, I'm biased.
Yeah. I have a bunch of questions, but I think I'll just ask this one for now. What determined the size of the James Webb? Did you guys say, we gotta make this as big as possible?
That's a good
We gotta make it small enough to fit in that cryo chamber? Like, how did
So-
you determine that?
So again, back in 85, when they started thinking about what we want to do after Hubble, this is 5 years before Hubble gets launched. What do we want to do? We want to do infrared. We know the infrared is going to be where things are going to be. The earliest stars and galaxies are going to be way back and redshifted back because of how far away they are. So it's going to be well redshifted out of the optical into the infrared for doing imaging, spectroscopy, any of that stuff. So it has to be an infrared cryogenic temperature. It's got to be cold because otherwise Hubble's at 300 degrees Kelvin. I mean, it's a room temperature. And so you can't use it very well in the infrared at all. Plus it's only 2 meters. So first thing was, it's got to be cryogenic. It's got to be at L2. It's got to be at least 4 meters in diameter. And then a little funny thing happened. The universe came along and changed how far the furthest galaxies were away.
Because of expanding space or what?
Just because the fact that we hadn't we used to think the universe was 13.4 billion years old. Now it's 13.7 or 13.8. Now we used to think there can't be any stars and galaxies early on. They've got to evolve and gas has got to come together and it's got to form. And you'll be lucky to see anything that's, 500 million years after the Big Bang. We're seeing stuff that's 300 million years after the Big Bang. And we don't have a clue as to what's forming those galaxies right now. Yeah. It's either lots and lots of stars going through an evolution very, very fast, or it's very, very big stars burning very fast, or some combination of both. We don't have a clue yet. We haven't got enough spectral analysis to be able to understand that. So we went from 4 meters to 6-ish meters. And then our NASA administrator at the time, another great story, Dan Golden said, why 6? Go to 8. So we kept hemming and hawing because, we got to package this thing into the fairing of an Ariane 5 launch vehicle. So you got all the constraints of how much. One of the designs, there were 2 big designs that were competing for the contractor of this job, Northrop Grumman and I remember the name of the company up in California. It wasn't Boeing, it was anyway, whatever it was. Oh, Lockheed Martin. Lockheed Martin and TRW, who's then Northrop Grumman. So one had the folding wings, which said, hey, if the wings don't ever work, you at least have all the central section of the mirror, 6 meters, 6.5 meters in one dimension, smaller in the other. You can still do great science with that. The other design had all one size mirror and not any folding stuff. So that limited to what they could do with that and what they could fit into. But the universe just changed. We knew we had to go back further. So it was 6.5 meters, had to be cryogenic. And then all the instruments were pretty much the way they were designed, except sometime, 20 years ago, somebody discovered an exoplanet. I mean, what stupid thing to do, go find a planet around some other star. And all of a sudden, now everybody wants a coronagraph on James Webb. So they added that. So fortunately, we had years of, we didn't get launched in 18. Well, 18 came and went. But the original date was 12, 13, 14, something like that. I can't remember when it was. I wrote a history of JWST from 1998 when we signed the formulation authorization document, which is the document that says you can start the project. We signed that in 98. Ed Weiler, who was the associate administrator, and I knew we could not get the administrator, Dan Golden, to agree to sign off on our formulation document if we said anything was realistic about the price. So we said, yeah, well, I just have to say it's $50 million. Or, in $97 or whatever it was, and only for phase CD or, whatever it happened to be. And it was $900 million, everything except phase E, which is the operational phase. And he and I knew that that's the only way we could get it past Dan Golden, because he was on, let's see, faster, better, cheaper. Those were his motto, right? Pick two of the three you can do. You can't do all three. Okay. So we said, all right, that's what. I have been crucified so many times by saying, you told us in Senate hearing, you told us it was going to be $500 million. And now it's now 18, or it's now, 8 point something billion dollars. So, it all happened. But again, the universe sort of forced us to go to 6.5 meters. That's something that we initially, 4 was the baseline design. The goal was always 8. And wavelength was another thing. A lot of them, people didn't want to go into the mid-infrared. There's nothing in the mid-infrared to see. Well, geez, if we weren't in the mid-infrared, you wouldn't get any of that data, spectra data, on those things that are way far back.
Let me ask a follow-up question real quick, Rick. So the size and shape of the heat shield,
Yes.
limits where you can point the thing. Why
Yes.
didn't you make that bigger?
So again,
It's soft, right?
it's soft structure, so it's not heavy. It's not a weight. But think of all the pulleys and cables that you have to do to pull that thing out and tighten it to the right shape in 1G and know that it's going to work in 0G. You can't have any of those layers ever touching, because then you've got a thermal short. So even in close to the spacecraft, the mirrors that are closest to the center of where the telescope is, center at the bottom of the telescope, where the spacecraft is underneath, those are the hottest mirrors. The coolest mirrors are the ones that are all the way out, which makes sense. But you can't have all those different layers come together in the central core. So they do eventually touch each other, but way into the center behind the spacecraft. But out to the edges, you can't have them, the layers touching a thermal short. So you can't have any of that. So that's one of the things. You can't make it too big, because then it becomes unwieldy, figure out how to get all the cabling and pulleys and tensioning systems. I mean, you just wouldn't believe the amount of pulleys and tensioning stuff that we had. We had problems on that Sunday. We deployed it once, and a cable got hung up someplace. And we find a kink in the cable, because, well, where'd that kink come from? And we have to go back and look, which pulley did it go over the wrong way? And why didn't it jump? How did it jump the cable way out here? And it didn't tension the way it was supposed to. And so we ended up building literally dog houses, little dog houses about this big, out of composite structure, to go over some of these cables to keep them from hitting each other as you deploy stuff. Soda straws. So we have some stuff areas where we have a soda straw that's got a spiral wrap cut along it that you can then spiral wind around some of the cables. The cable moves inside of the soda straw, but doesn't jump over to the next pulley. I mean, just insane things like that we had to do very late. I mean, within 3 or 4 years of launch, there are problems that we had to fix. So it's just limited to how much you can do. Now, micrometeoroids. We had that big one, right? Everybody goes, oh, geez, this thing's going to last for 20 years. You're going to have these micrometeoroids hitting everything all over the place. They're going to lose the mirrors and all that stuff. So they sat down and analyzed it. We go, let's not look into the RAM as often as we did the first year. So for the second cycle, they have now developed an angle, which is 75 degrees cone around RAM. We only can observe in that cone 15% of the year. And that's got to be a really reason why you got to do it. High science value, got to look at it, you know, whatever the answer is.
Again?
What? RAM is the direction that we're flying into.
Yeah.
So stuff's coming this way from who knows where. So, so I go, wait a minute, 75 degrees, it's a huge angle, a cone angle. That seems way too big. So I'm talking to the system engineer. This is a couple of months ago. And he goes, I said, wait a minute, wasn't that really big one? Weren't you looking straight up north and straight up or straight south? And he says, yeah, it was somewhere in that 2-day period. We know it, we got that big hit by that micrometeoroid. I don't know when it was because they only do the sampling every 2 days of the wavefront error. But somewhere in that 2 days, most of that 2-day period, we were looking either straight up or straight down. I can't remember which. Nowhere near the RAM direction. So I'm going, why are they so upset about, why are they zeroing in on 75 degrees for a cone when that big one was nowhere near that angle? So this is a continuing discussion that we will have with the science community, because they're all going to come back and say, oh, we really didn't want to mean 75. Let's tighten it up, go to 35. Maybe 35-degree cone is okay. So we think there's going to be a lot of buyer's remorse on the third cycle because of that. I mean, you know, so we're dealing with that all the time. So the best analogy is you buy a brand new car, the first time you get it scratched anywhere on the car. Oh, geez, that stupid car is not worth what it was. This thing's never been the way it was since before we launched it.
All right, one more question. Anybody got one more question?
Yeah.
What Dr. Webb?
So,
Oh, yeah.
so back several years ago, I was asked by the director of astrophysics at headquarters to lead a team to look at the 4 big missions that we were proposing for. Let me back up one. Every 10 years, the National Academy of Sciences does a decadal survey of space-based and ground-based astronomy. So the National Science Foundation, NASA, and originally it was the DOE, but they have their own thing now. So NASA and the NSF, and they have a whole bunch of scientists. They put panels together. They work on this for a year and a half or so, and they come up with, here's what you should do, NASA, for the next 10 years. The next big observatory. These are called strategic missions or flagships or whatever you want to call it, but big bucks. What you need to do to keep the smaller explorers going, the smaller missions going, what you need to do to keep the community grants program going, and you know, things like that. And what you need to do on the ground. And the ground is the 30-meter telescope, and it's hopefully going to go in Hawaii. That'll be, they haven't gotten the permit yet to build that. That's another story. Because I finished building the Caltech 1-millimeter telescope in Hawaii, so I dealt with the native unrest, let's put it that way. Anyway, there's that decadal every 10 years. So ahead of the decadal, they asked me and my team, a little review team that we put together, to sit and look at the 4 big concepts for the big missions that were sitting to go after not just JWST, but after the Roman Space Telescope, which is a wide field, smaller telescope. I think it's 2 meters, 2 meters. So 2-meter sized mirror, but it's a wide angle telescope. So it's going to be a real looking at very, very large fields to try and understand dark energy and dark matter. It's the whole main purpose of the Roman Space Telescope. That's the next one. And the question is, what do you do beyond that? So there's a large exoplanet type mission. There's a UV ultraviolet mission. The ultraviolet community hasn't gotten anything in a while. You know, it's like everybody's got to get a little bit of something. Hubble has the optical. We have infrared. Maybe they'll get something. The X-ray people would like to get something to surpass Chandra, which has been up for years and still doing great science. So those 4 missions were all put together as concepts, and we analyzed and we reviewed, because these are just, I mean, these are what we call pre-concept level. They're so early on, you don't have a clue what the real costs are. Barely have an idea of what the technologies you need are going to, you know what the ones are that you're going to need. No idea how to make them. It's like these 10 ones we did for JW. They were all inventions. None of those existed before we did James Webb. So we looked at all that stuff, and I refused to put a price tag on it. I said, I'll bin them. So we binned them $6 to $8 billion, $8 to $10 billion. plus $12 billion sort of range. And we sent that into the National Academy of Sciences, and they came back and said, the next big thing they want NASA to do after Roman is a big, what's now called the Habitable World Observatory, HWO. I always want to say WHO, but it's HWO. And they're beginning to pull together between JPL and Goddard a concept for how big this thing would be. It's going to be a visible, warm, get away from all those cryogenic sunshades, warm telescope, 6 meters, maybe 8 meters in size, with a tube around the front of it, like you build your ground-based telescopes, a big tube around the front that's deployable to keep all the sun out of it so that you don't have to mess with sun hitting the secondary mirror and the primary and all that good stuff. And highly precise optics that allow you to do high contrast imaging. So high contrast imaging is, here's a star, here's the planet I want to look at. Now, the best way to do it now is to look at stars that are dim to begin with. So you look at brown dwarfs. That's the best thing to do right now, because the planets could be in, could be fairly close in to the star and yet still be in the habitable zone. But if you want to look at other type, like a G-type star, like the sun, you're going to have to cancel that bright central star out to the order of 10 to the 11th. Okay, 10 to the 11th, 10 with, 11 zeros after it, in order to be able to cancel out that bright central star and see the planet enough to be able to look and do a spectrum of the atmosphere and tell whether there's, the right gases in it to support life. So one thing I said, and I did this at the hearing we had, when was ever that was 2011, I guess, 2011. The hearing I had, one thing that I wanted to get across to the people about James Webb is, in 10 hours of observing with James Webb, I can tell you whether or not there's methane in the atmosphere. If it has an atmosphere, if the planet has an atmosphere, if there's methane in it, 10 hours is observing. All I need. So that's where we are. The next thing is going to be Habitable World Observatory. Is what, if they win that concept. The X-ray folks are still trying to do their X-ray mission. So who knows where it's going to be, but that's where we are.
Wow, well, that was spectacular. Thank you.
Thank you very much.
Thank
you.
Enjoy talking about this stuff.
It shows.
Come back in time.
Yeah.
So what was the NASA, JWST has a James Webb historian, who's Canadian, works with the Space Agency, and he's been interviewing me and a bunch of other people trying to get the history and timeline. And he goes, so how do you survive an asteroid in this stressful environment? I said, you've got to get along with. Gotta get along with anybody, including the people you can't stand. Make sure you can't stand. You just gotta both work. I gotta work with these people. I gotta get stuff done. And they have to, do what I need to do. Second thing I do is, I always, I have a phrase that I always put by, which is, you got it. 3 times a year, you're not doing stuff. So my goal is to get the mission out of it.
Yeah.
And the other thing you have to have, is you gotta have a good sense of humor. We go crazy. Is that readable or that's just something you did for yourself? No, that's